This, can I get rid of this?
Which one?
This one here.
No, no,
No,
hide.
hide.
No, no, not stop sharing. Hide.
Ah, sorry.
Click stop sharing.
We said there was an option to hide.
There is an hide.
Ah. Yeah.
Yeah.
Huh?
Yeah.
Okay, so sorry for the technical delays. So we are very happy to have Ilias Kotsireas from Wilfrid Laurier University in Waterloo visiting us. So he was planning to visit us during FIPSAC, but for various reasons it could not happen. But now he's here finally, and he will talk about Legendre Pairs, his current activities.
Thank you very much, Arvind. I'm grateful for hosting me. Every mathematician's dream, obviously, is to visit India, because every mathematician, beginning as a student, learns about Ramanujan and later on about Harishchandra. So for me, it's like a pilgrimage, to visit India for the first time. And I thank you all for coming to this seminar. And before we start, I have a small quiz. Some mathematicians are birds, others are frogs. Birds fly high in the air. They survey broad vistas of mathematics into the far horizon. And that is reminiscent of this well-known Escher painting, Day and Night. And I've seen many Escher paintings here in this building. So this essay goes on, and basically the main premise is that mathematics needs both birds and frogs. And mathematics is rich and beautiful because birds give it broad visions and frogs give it intricate details, technicalities, and so on. Quiz: who wrote these words? Thank you very much. So this is a delightful essay by Freeman Dyson, of course, appeared in the notices of the AMS in 2008 or 2009. And these are two of his birds, Francis Bacon and René Descartes. Yuri Manin is another one mentioned later on, and many other ones. It's a very nice read if it's serious mathematics, and also this nice metaphor. I'm a frog, obviously. So let's continue on with Legendre Pairs. There are some ingredients that we need to define Legendre Pairs, and the first ingredient is this one here, the periodic autocorrelation function, abbreviated as PAF. So what it is that you take a finite sequence, A0, An minus 1 of length n, and you define the periodic autocorrelation function coefficient, this PA of S, to be this sum here. So the sum is from 0 to n minus 1, AK plus S, where K plus S is taken modulo n, so that you stay in the indices 0 to n minus 1, obviously. And there are some properties which are important of this path function. The first one is that if you have a circulant matrix is one that is defined by the first row only. Every other row is a right cyclic shift of the first row. So it's a special case of Toeplitz or this kind of structured matrices. So if you have a circulant matrix with first row the sequence A, then this path is the inner product of the first row of the circulant and the ith plus 1 row. Then there is a symmetry property. PA of S is PA n minus S for every S in this range. And that tells us that when we deal with the path function, it's enough to use half of the path coefficients. The other half are equal to the first half. And there is the second DSF property, elementary symmetric function. If you take the sum of all of these path values from 1 to n minus 1, then this is twice the second elementary symmetric function in your variables. Okay, and the second elementary symmetric function, of course, is an object studied extensively in combinatorics. The second ingredient and last ingredient that we need is the familiar discrete Fourier transform.
Sir, could we go back?
Yes, of course. Yes. So there are these three properties that come into play later on. Well, only two come into play. The third one is as of yet unexplored entirely. So this connection with the second elementary symmetric function is still. Thank you. The second ingredient is the discrete Fourier transform. So the discrete Fourier transform associated to a sequence of length n is another sequence of n complex numbers, mu0, mu n minus 1. This is the usual definition, with omega being this familiar primitive nth root of unity. So this is something very, very classical, right? And when we compute this DFT associated to a sequence, then we take this new case, the elements of the DFT, we take the squared magnitude, so the sum of the real part and the imaginary part, and we call it the PSD, the power spectral density coefficient associated to this sequence at K. Okay. So PSD is a very overloaded acronym. It means positive semi-definite, postdoctoral fellow, and I don't know, and so on. Anyway, there are many other.
Notation you should, it was A0 to n minus 1.
Yeah, these are equivalent. It can be either from 1 to n or from 0 to n minus 1. It's the same thing.
No, in particular, no, you're saying A0 to n minus 1, so that's over the n, it's over n, not over n plus 1.
Over here?
The number of terms in the sequence is 1 less than the previous time.
No.
Yes, but it's
A0.
Is A to the n minus 1.
but here I have a I
No,
plus
that's
1,
right.
right? So,
If there were n
yeah.
terms on the previous
It is in the previous slide. You're right. It was from 0 to n minus 1.
same number.
Yeah, but it's the important part is the indexing is modulo sum. Translation is equivalent to equivalent indexings, let's say. But the point is, it's length n always. Okay, so these are the two ingredients, and with these two ingredients, we can give the definition of these objects, the Legendre pairs. It was given by Jennifer Seabury in 2001. Jennifer Seabury is an Australian cryptologist and cryptographer and design theorist and all the rest, who discovered these objects in 2001. So for every odd length n, if we have two sequences A from A0 to AN minus 1 and B respectively, where the elements are only allowed to be plus and minus 1, then they form a Legendre pair of order n if the periodic autocorrelation function value of A at S plus the path value of B at S is equal to minus 2, and this is true for every S from 1 to n minus 1 over 2. In other words, we have this n minus 1 over 2 quadratic equations that has to be satisfied in this space of minus 1 plus 1 to the n of sequences of length n. Typically, we also use this normalization that the sum of the elements in A is equal to 1, and the sum of the elements in the B sequence is also equal to 1. This is a technicality because it's easy to prove that these n minus 1 over 2 equations, they imply that the Diophantine equation A square plus B square is equal to 2, where A is the sum of the elements in capital A and B is the sum of the elements in capital B. Therefore, the only solutions are plus minus 1. And from the four possibilities, we choose this one just to, to do this normalization, which also helps to get an upper bound of potential A and B sequences and choose n plus 1 over 2. So this looks like a scaled Catalan number, if you like, or n minus 1 over 2 here. These are equal, obviously. Now there is a so the path, if you like, is an invariant of these Legendre pairs. If you add the coefficients for every s, you get -2. But there is another invariant, which is a consequence of the Wiener-Kinzin theorem from information theory. The Wiener-Kinzin theorem says that the DFT of a sequence is the path, the sequence of the path values, and vice versa, the inverse DFT of the path sequence is the sequence of the PSD values. So using that theorem, we can prove that the PSD values of A and B, if you add them up for respective S, they are equal to a constant. Again, only now this constant depends on n, the length of the pair. So we have this equation for every s from 1 to n-1/2. So to summarize, you could say that Legendre pairs are characterized by the constancy of two invariants, the path and the PSD invariants. The path constant is -2 and the PSD constant is 2n plus 2. Okay, so it's a very simple definition.
Sorry, I forgot to note down the definition of PSD. What was so you
The-
explained the discrete Fourier transform?
Yes, that's right.
So
The PSD here is these are the values of the DFT.
yeah.
Okay, for each, these are complex numbers in general.
Yeah.
In some cases, they're integers, which is interesting, but in general, they're complex numbers. So we take the square magnitude of those for every k, and this is the PSD at argument k.
Okay, so you can form a tuple, an tuple of PSD.
Yes, yes, exactly. And you do the same for the B sequence. You compute the PSD values of the A sequence and the B sequence. And if you add them together for specific S, the sum is always an exact integer. So even though these are floating point numbers, the sum is an integer in exact arithmetic, which is a huge constraint, a very stringent requirement.
And this is
If
it
you
and
like.
only.
This is even only, yeah. So Legendre pair, the summary is that Legendre pairs are characterized by these two invariants. One invariant with the -2 value and another one with 2n plus 2.
So, okay, so if you know n and you know path plus path, then you know PSD.
Yeah, so if you know path, you know the PSD, and vice versa from this Wiener-Kinzin. You can take, if you have the sequence of path values, you can take the discrete Fourier transform, and it will give you the sequence of PSD values. And vice versa, if you know the sequence of PSD values, you can take the inverse DFT and recover the sequence of the paths for each sequence separately. You do that for each sequence separately. And the point is that the sums for a specific S, they always sum up to a constant. For the paths, the constant is -2. For the PSD, the constant is this 2n plus 2. So it involves the length of the sequence.
So is this not possible for even n? Is that
No,
why?
no, they don't exist for even n.
And so in particular also, if you know it's a Legendre pair, then the PSD tells you what is n.
Yeah, okay, yeah, of course. If you compute this, then you know automatically you find n. You subtract 2, you divide by 2, and you get the n. Indeed. So some examples, just to make things more concrete, as if they're not concrete enough. But, it's useful to see some examples. So for n equals 11, LP11 is given by, for example, by these two A and B. The PSD constant is 2 times 11 plus 2, so 24. The first 5 path values, so 11 minus 1 over 2, because of symmetry. The first path values are -1, etc. Then the first path values for B are -1, etc. Vertically, all of the sums are equal to -2. So we are done. This is a Legendre pair. Then LP13, PSD is 2 times 13 plus 2, 28. This is A and this is B. There are many other solutions. This is just one solution. The first 6 path values are 1, 1, -3, etc. The first 6 path values for B, this is for A, this is for B. the sum is always vertically minus 2, 1 minus 3, minus 2, 1 minus 3, minus 3, 1, and so on. So the sum vertically is always minus 2. Okay, so that's some simple examples of Legendre.
So the symmetry
Yes.
will also go to the last 6 values, but then the middle value may not be this. Some of the 2 middle values.
No, all of them have
You
to
avoid
be.
0.
N is odd. N is
You avoid
odd,
0.
always.
S equals 0.
No,
I mean, it's like, so first,
Yeah, no, this is
first
a
5,
good
last 5, and then there's the one in the middle. First 5 will be the same as the last 5,
mhm.
right? Like, okay, that's so.
Well, look, 13 minus 1 over
These
2
are second
is,
He's talking about the
values,
top
not
one.
the first one.
oh, this
First
one.
is S equals 0, you
Oh, I see.
don't want S equals 0.
Yes,
Second
S
to
equals,
6 and
so let me, I should have mentioned this, sorry, over here. So for S equals 0,
will be all, yeah.
over here, we get the sum of the squares of the sequence. And because these are plus and minus ones, this is a constant that will never be equal to minus 2, obviously, so we discard it. We don't use, and in the definition of Legendre pair, there is no 0, right? It starts at 1. So we go from 1 to n minus 1 over 2, and we take the half of those, half of these values. So over here we have that n minus 1 over 2 is 10, so we get the first 5. And first 5 means path at 1, 2, 3, 4, 5. The other ones are equal to this first 5. PSD 0 obviously is equal to 11. The sum of these elements here, the squares, is 11. So we don't use it because we know it's, yeah, the path at 0 of this sequence is equal to 11. It's the sum of the squares.
And the PSD at all of those values is 12.
Yes.
But downstairs, what is the PSD? The PSD, of course, is the same.
Well, here is a bit different.
Varies from
We will
three
do
elements.
an example, of course, with I didn't list the PSDs here, but I will list it in the next example. So 37, PSD is 2 times 37 plus 276. This is A and this is B. The first 18 path values, again, minus 3's, 1's, and minus 1, 3, and so on. And again, the vertical sums everywhere are minus 2. But now I also listed the PSDs just to show what they look like. I listed only 18 of them for the same reason as the paths. The other 18 are equal to the first 18. So we start at S equals 1. We get this 25 point something for A, and this is for B. The sum is equal to 76 exactly. And this is something that you can prove. It maybe involves some trig manipulations or whatever, or you can do it more cleverly using complex numbers. But either way, you will get this 76. It's a useful, exercise to try it out and convince yourself that you get 76 exactly, not numerically. Although these values are numerical, so there is error in the computation, whatever. The sum is an exact integer, 76. So amazing property. Then for 2, we get the 50 and the 25, which are the same but inverted, if you like, 76, and so on all the way down. Of course, this is not a coincidence, but these values are the same. It's because we have these values, which are only minus 3 and 1. So you can see, again, using the Wiener-Kinsin theorem, you get this pattern, which is the same as this pattern of minus 3 and 1s. Okay. So this is how the PSD invariant materializes in a computational example. Okay. Here is a bigger example, LP55. Now the PSD constant is 2 times 55 plus 2, 112. This is A and this is B. The first 27 path values are minus 9, 3, minus 5, etc. And underneath 7, minus 5. The sum is always minus 2. Okay. Yes, the path is always always odd for these sequences anyway. And the point here is that if you look at this example, these are 55 binary variables, and this is another 55, so total 110 binary variables. So this object is not too easy to compute, if you like, right? And yet, here it is. By the way, 55 is not a prime. All the previous examples were primes, so you would think that they're easy to find, and you would be correct, as we will see in a minute. But 55 is not a prime, and we can still find Legendre pairs for this length.
Did you say for primes finding these are easy?
Yes.
Okay. And then from primes, can it construct?
To composite. Yeah. For prime to composite, it's a lot harder.
Oh, it is a lot harder. It's not
Yeah,
hard to
yeah.
say backwards.
Unfortunately, no. Nobody knows anything.
Oh.
So here is why they're easy for primes, and this also justifies the name Legendre pairs. It turns out that Legendre pairs of prime lengths, can be written down by a Legendre symbol construction, which is very, very simple. You can do it in 4 lines of Maple code, if that can be called code here. So with number theory, you load the number theory package in Maple. You take the sequence of Legendre symbols I over P from 1 to P minus 1. You use this sequence and you prepend 1. Then you multiply this sequence by minus 1 and you prepend it with 1. And this is A and B. So A and B is a Legendre pair of length P for every odd prime P. So you are done with the primes. For every prime, you can write down the A Legendre pair. There are many other ones, but you can write A Legendre pair AB in few lines of code using the Legendre symbol from number theory, which tells you whether something is a quadratic residue modulo this denominator here. However, not all primes are the same. The parity modulo 4 of primes is an important property, because what happens for primes that are 3 mod 4, we have seen the example for 11, all the path values are equal to minus 1, all the PSD values are equal to P plus 1, so if we sum them up, we get the minus 2 always, and the PSD constant to P plus 2, twice P plus 1. But for 1 mod 4, well, things are a bit more interesting. All the path values belong to this 1 minus 3. There are only 2 different PSD values as a consequence, and you can write down a formula using the Gauss sum. And this is something that I learned from a number theorist that I started to work with recently, Arne Winterhoff, who's a number theorist at the Austrian Academy of Sciences, when he looked at these examples, and he told me right away, but come on, this is the Gauss sum. I mean, you didn't know that? And I didn't know that. But anyway, now I know that it is, it's given by this Gauss sum formula, and with some manipulations, again, you can prove that the path constant is always minus 2, and the PSD constant is, as it should be, 2P plus 2. So for primes, this problem is solved entirely. But for...
Sorry, just to clarify.
Yeah.
You said that you can construct the Legendre pair using the Legendre symbol.
Yes.
But are they the only ones?
No. So if we go back here, this is A,
Yes.
A Legendre pair of
Yeah,
length
that's
P,
what
but there are other ones.
Which are not obtained from the Legendre.
No, they are obtained computationally. So there are, of course, exhaustive searches up to all n equal 25 to find all of the Legendre pairs and study them with data science methods. What else would it be nowadays? But anyway.
So is it true that this is the only systematic, non-computational way how to find Legendre pairs for prime?
No, there is another one.
There is another recipe.
But not for primes, for another class of orders. Yeah.
Is this required by Taylor construction?
For Hadamard? Well, it's very related. Yeah. And of course, where this is going is to Hadamard, as you said. So
And behavior P mod 1 mod 4 and 3 mod 4 is for this construction.
exactly, yes, only for this one. Yeah. For any prime P, there are other Legendre pairs that do not come from this. They're more random, if you like. They don't come from this formula with the Legendre symbol.
And you mentioned the other class of integers.
Sorry, there's a systematic risk.
Well, there is another case that I will
You will.
come to. This is here. The twin primes. The twin primes construction is the following. For every twin primes, P and P plus 2, there is a Legendre pair of order P times P plus 2, the product. Okay. Now, there are two caveats in this construction. The first one is that it sort of encompasses the twin prime conjecture that everybody believes. Obviously, everybody believes there are infinitely many twin primes, but no one has proved it. It's famous open conjecture in number theory. So if we believe the twin prime conjecture, then this construction gives an infinite class of Legendre pairs and Hadamard matrices. I will come to those in a minute. And the second caveat is that this construction requires that the twin primes must have a common primitive root. A common primitive root, because this is used in the construction. And this is another open problem in number theory. So we don't know a counterexample. We don't know any twin primes without having a common primitive root.
Yeah.
A primitive root mod P is something defined in number theory. It's a number theory concept, like the Legendre symbol. I don't remember the exact definition.
Is it like the generator of the cyclic
Something along those lines.
It is that.
What is it?
Thank God for them.
The
Yes.
multiplicative group modulo P. Okay. It's cyclic, so it has a generator. Any generator is primitive.
Yeah, thank you very much.
And they have the same number. Is it?
Yes.
Yes, exactly. But they must have a common primitive root. So there must be an integer which is the same for both P and P plus 2. And so if we say that this is G is a common primitive root of P and P plus 2, then the length of the Legendre pair is this product. We define this upper bound to be P squared minus 3 over 2. Then the positions of the minus ones in the A and B sequence are encoded by these numbers, j to the I mod n, from 0 to this upper bound, and the rest is I times P plus 2 mod n again, from 0 to P minus 1. And this is A, and underneath you take the same to be B, and you have the path values are over here plus minus 1, all of them. Underneath the same thing, minus 1, the sum is minus 2, and you are done.
So this was the values, these are the minus ones in A, and the rest in A are ones.
Yes,
What is B?
exactly.
B is the same as A?
B is the same as A.
Oh, B is the same.
So like in the prime P 1 mod 4 example, A is the same as B.
Ah,
So this is the twin prime construction. Again, modulo those two interesting caveats. It seems to work. You can try it for every P or P plus 2 for any twin primes you like. You will always find the G. I have the code for that. I can give you the code. Of course, you don't have to do everything from scratch. You will find the G, and then this is easy to write down, and then to check it, it's a few seconds in Maple. So this, of course, is a theorem. It's proven in some paper several years ago. And now let me come briefly to the Hadamard conjecture because it's related to this construction of Legendre pair. So in 1893, there is a Hadamard matrix of order 4n for every n from 1, 2, and so on. So essentially for every multiple of 4, excluding the trivial cases, the orders 1 and 2. After that, for every multiple of 4, it is conjectured that there is a Hadamard matrix of order 4 times n. This is an open conjecture, probably one of the most famous open conjectures in discrete mathematics anyway. And it's a necessary condition. The zero mode 4 property is a necessary condition. The sufficiency is the Hadamard conjecture. So the necessary condition is very easy to prove. It's a simple combinatorial argument. You can find it in any combinatorics book. But the sufficiency is the Hadamard conjecture, that they exist for every multiple of 4. So the computational state of the art is that until 1985, it was not known whether or not the Hadamard matrix of order 268 exists. And this person here, Savade, found one in Graphs and Combinatorics paper. Then until 2005, so about 20 years, the next smallest order, the 428, was found by these two mathematicians in a JCT, Journal of Combinatorial Designs, Alzheimer's. In 2005, then my co-author Djokovic found this HM764 in 2008 Combinatorica, and myself with two other co-authors again found this 1004 in this JCT 2014 paper. And Shalom Eliyahu has a very interesting survey in French in this CNRS free math encyclopedia website, Image de Mathématiques over here.
It's in French.
It is in French, yes. But the math is quite readable. So here's the connection. Yes, sorry. Yes, sorry.
Just out of the curiosity, since you wrote down 1004 proof, like how does that paper look like? You don't usually mention a million zeros.
Yes, how does it look like?
How do you prove it's orthogonal?
Yeah.
You
Yeah.
give the code.
It uses no, it's not. We don't give the code. The code is let's say under IP. What we do is that we use the method of orbits. There's something called the method of orbits, where you take a certain action of a multiplicative subgroup or of a suitable group, you enumerate the orbits of this action, and then you take unions of those orbits. And then you end up with 4 very large data files with all this information. And in all of these, so by large data files, I mean these are 4 data files. Each one of them is about 10 million rows and 50 to 60 columns of integers. And in this volume of data, you find 4 rows that when you add them vertically, you get the same sum. And that gives you this solution. And the contribution of the middle author here, this Golubitsky, is that he wrote the code to solve this problem, which is clearly a big data problem, if you like. This is not combinatorics. You are given or math. It's a hard computer science problem, and in particular big data. These are huge files, but somehow in all this mess of deluge of data, he managed to find this, what we asked him to find, and then we just read off the solution from this solution that he found. So there are many technicalities in that paper, very many, but it is doable, and also it is reproducible. It's a reproducible result. As opposed to this paper here, which is not reproducible, unfortunately. So
What do you mean it's not?
I mean that I tried many times to reproduce it, and I failed to reproduce it. To write the code to find this one here, using the method that they are describing in that paper.
But so you don't believe that there is a...
No, the result is correct. There is no doubt. The result,
matrix they provide is correct.
of course.
How they got to
But how they got to it is, I couldn't get to another one. Let's say you want to compute another one, just to debug your code and whatever. I was never able to do it. So anyway.
But this other thing you mentioned, the smallest open order.
Yeah, so I forgot to say it. Thank you. So the smallest three open orders than 1,000, smaller than 1,000 still open is this three here. And this is the most famous one, the 668, that people try to find it, but so far it's of course it exists. There's no doubt. But to find it is another story. Well, yeah, you can say that it would be a counterexample. If you can prove that this doesn't exist, then you destroy the Hadamard conjecture, which is also a big deal. Yeah. Obviously, but most people believe that they exist for every multiple of 4.
So wouldn't it? I'm just confused as to why you tackled a much harder problem of 1,004 as opposed to 668.
Well, because it was open and because we could do it.
No, but what your techniques were?
No, unfortunately, no, because this here is 4 times 167. 4 times 167. 167 is a prime 3 mod 4. These are the hard primes in the Hadamard conjecture, and there is no convenient multiplicative group or subgroup in there. While here there was one. There was a nice suitable subgroup of order 15. And here there is no such thing.
Inside what Z 1000%.
Yes, yeah, that's the space that we worked on. Yeah. So convenience, let's put it that way. We tried, of course, all of these three with this method, the union of orbits, but to no avail. So the connection of Legendre pairs and Hadamard matrices now is this one here. If you start with a Legendre pair, AB, you make 2 circulant matrices, CA and CB. So CA has the first row equal to A, and CB has the first row equal to B. Then you take the transpose of the circulant and minus the transpose of this circulant. Then you, if you look at this, this has this block here, 4 by 4 block, 2 by 2 block, if you like, has order n by n. Then you supplement it with this pattern of plus and minus ones over here. So pluses over here, pluses and minuses, and this 2 by 2 block. And now this is 2n plus 2 by 2n plus 2 matrix. And this is a Hadamard matrix. So for every Legendre pair of order n, you make a Hadamard matrix of order 2n plus 2. So in particular, we know how to construct Legendre pairs of order p for every prime p. Therefore, that gives us an infinite class directly of Hadamard matrices 2p plus 2, which are probably very related to your Paley question, right? Over here, Legendre pairs p plus 2 give us Hadamard matrix of 2 times pp plus 2 plus 2. If you believe the twin prime conjecture, obviously this is another infinite class, and this is what we know so far. And now, if you think about it, the odd values of n cover the full spectrum of multiples of 4. Okay, so 4, 8, 12, and so on, they are all of this form, 2n plus 2, or n odd. Therefore, if we know how to make a Legendre pair of order n for every odd n, then we have this structured version of the Hadamard conjecture. In other words, we can provide a solution to this Hadamard conjecture, but via this very structured form of Hadamard matrices, because in the literature of Hadamard matrices, there are hundreds, literally hundreds of different constructions for Hadamard matrices, but they all have the same problem. They don't cover the full spectrum of multiples of 4, except supposedly or arguably this one here. This one here. So far, there is no counterexample. There is no counterexample so far. There are open cases, of course, Legendre pairs, but there is no counterexample of a certain odd number for which there is no Legendre pair. There is no result like that and I don't think there will be. Who knows? But that's my own intuition, if you like. So this is the connection. This is the motivation for introducing these objects, because we can make Hadamard matrices, and we can make, arguably, we can make all of them for every multiple of 4. So for primes, remember that for primes, we know how to, this sequence of orders is very sparse within the set of all multiples of 4. So these are useful, but they're very far from resolving the Hadamard conjecture. So we have to focus on composite values of Legendre pairs, and in this context, we prove the theorem with my co-author Djokovic, who happens to be from the University of Waterloo. So it's the University of Waterloo the campus is 200 meters from my own university, so it's very useful to collaborate with people from over there. So we have a paper in 2015 in DCC, Designs, Codes, and Cryptography. This is what we came up with. If A is a sequence of V elements, and V is a composite number, let's say D times M. So no, V is not a prime anymore. It's a composite. We choose some factorization. D and M don't have to be prime, any factorization. And we look at these subsums of elements of the original sequence, which are D apart. And we do that, so AJ plus AJ plus D plus etc. plus the last one. So we keep adding multiples of D in the indices. And we do that for every J from 0 to T minus 1. Then we define this new sequence, A parenthesis D, which is this sequence of D subsums, and we call it the M compression of A. So why do we do that? Well, because we can prove some useful property that if we have a Legendre pair AB of length V, which is composite, and we M compress A and B by the same M, then we get these two sequences here of length D. Now the alphabet is from minus M, minus 2, etc., minus 1, plus 1, up to plus M. And it turns out that these two sequences, they have a property which is similar to Legendre pair, but not exactly. The sum of the paths of these two compressed sequences is equal to minus 2 times M. M is the compression factor here, for every S from 1 to D minus 1 over 2. And the sum of the PSDs is 2V plus 2. And this is exactly the same constant, PSD constant, of the original Legendre pair. So in other words, this operation, if you like, of M compression has the effect that the path constant scales linearly, minus 2 times M, while the PSD remains entirely invariant. It's the same. And the gain, so why are we doing this? What do we gain by doing that? What we gain is that now we are dealing with a much smaller sequence, this one here, length D, instead of length V, which can be ginormous. Okay, and then this simple concept has many consequences computationally. Just to give a few examples here, LP15, Legendre pair for n equals 15, we can use these two factorizations, 3, 5, and 5, 3. The 3 compression gives us A5 and B5, and A5 is a sequence of 5 elements. You start A0, A5, A10, A1, A6, A11. You get the idea. It's very simple. The same for B. Now 5 compression. A3 is a sequence of 3 elements. The first one is A0 plus 3, A3 plus 3, A6, A9, A12, and so on and so forth. And B3 is this one here. Obviously, the sum of the elements of this sequence is also 1, because these are simply rearrangements of the elements of the original sequences. So they have the property that the sum is also equal to 1. And here's an example. LP 133. 133 is 7 times 19. You can compute the 19 compression of this Legendre pair, and you get these sequences A7 and B7, very small sequences and very small growth on the elements here, -1s, 3s, 5s, right? If you compute the puffs, they sum to -38, -2 times 19. If you compute the PSDs, they sum to the original PSD constant 2 times 133, 3 plus 2. But now here's how we use this compression technology, if you like. Suppose now that someone gives you this A7 and B7. So these are given. How do you recover the Legendre pair 133? This process is called decompression, and as of today, it's purely done computationally, so not theoretically. It would be nice to do it theoretically, but I have no clue how to do it. So this decompression is very expensive process. However, it's a lot better to work on a space of these sequences of length 7 rather than the space of sequences of length 133 to find Legendre pair 133. That's why we bother with this compression.
You can go back.
Yeah, you can go back from this one here, this small sequence and this one. These two, if you do decompression, you recover LP 133. But this is an interesting program to write. It's not. I would say it's not a trivial code to write.
But I mean, I don't use it. But your next point, you're saying compression is not one-to-one.
Yes. Yeah. Of course. So the second problem is that compression is not a one-to-one mapping, and that means the following: if someone finds some other sequences, let's say A tilde 7 and B tilde 7, that have these desirable properties, the sum of the puffs is -38, and the sum of the PSDs is 268, then it is not guaranteed that if you do decompression, you will yield this LP 133.
For example,
Yeah, many counterexamples. So
No,
you can
so
do.
you can decompress, right?
You can, but it doesn't mean that if you find sequences with the right alphabet, right, from -7 up to +7 elements. So, and this is a very small space. You can find out all of them exhaustively. But when you do decompression, you will notice that maybe 10% gives Legendre pair. The other 90% doesn't. That's why I'm saying it's not a one-to-one mapping. So if we have a Legendre pair, then it has to come from a pair of sequences of this kind. But if we have sequences of this kind, and by that I mean -38 puffs and 268 PSDs, then it doesn't mean necessarily that they will yield LP 133. So that's one of the caveats.
It's not even obvious that you could decompress. I mean,
there's always one, but the point is, saying they can sometimes they can none.
no, I'm not saying Legendre pair.
But what you are explaining is that it's not onto, right?
Yeah, yes, exactly.
Well, you can also say that onto, yeah. But I think one-to-one is also, it depends on the spaces, right? What spaces you work with. If you, so let me say it one more time, maybe hopefully being more clear and answering your question. So if you compute all these sequences A tilde 7, B tilde 7, with the alphabet from -7 to +7, -3 +3, and ±5, okay? With this property, puff is the puffs sum to -38, the PSDs sum to 268. Then this is one example of these sequences. If you compute all of them, then you can start decompressing all of them simultaneously. You run the same code, but only some of them will give you a Legendre pair. So if you have a Legendre pair, then by the compression, you get a sequence of this kind, a pair of sequences of this kind. If you have a pair of sequences of this kind, it doesn't mean that it will correspond to a Legendre pair. So some of them here are some of these pairs will be useless.
No, I understand that point
Yeah.
completely. I was behind you. I was just asking
Yeah.
that it's not even obvious to me that if, I mean, you're starting with two sequences of length 7 and you're building two
Yes.
sequences of length 133.
Yeah. But there are many combinations. to
Yeah,
do that.
so
There
it
are
was
many
not even
combinations.
clear that you could do that at all.
Well, yeah.
Oh, you're just doing exhaustion.
Well, LP 133 is very big, so
Yeah.
we're not going to do an exhaustive search.
No. I mean,
But we do
from
one,
this-
at least we find one.
No,
Legendre
so
pair.
you are given this A7 and this B7, suppose.
For these two, you can do an exhaustive search.
That's
Yeah,
right.
that's doable.
That's
Because if you think about it, this is how many terms? Plus minus 1, 3, 8 terms. 8 terms, and this is for each one, 8 possibilities, and this is 7. So 8 to the 7. 8 to the 7 possibilities total. That's a very small number. And the same for B. So this is, you can clearly do the exhaustive search of these sequences of length 7 from this alphabet and these two properties. That's, quite fast. Then from each one of these pairs, you have to do the decompression. And my guess is 10% of those will give you Legendre pair of order 133, and 90% give nothing. So it's not a one-to-one correspondence, if you like, between Legendre pairs and this kind of sequences. Or onto, if you want to use onto. Okay, so the same.
Another question. Suppose
Yeah.
I just take the sign of all the elements, so that.
Yeah.
So I replace all the
Yes.
negatives by -1 and positives by 1.
So you want to multiply by -1.
No, I take
No.
the sign of all the elements.
The sign.
Signature.
Yeah, okay.
So then I get.
Plus,
do I
plus,
get a-
minus.
Yeah, do I get a Legendre pair? Of size 7?
Of size 7.
But the last one is plus and plus.
Uh,
The rest are plus and minus.
No. Legendre.
Hmm.
I mean,
So you want to do this 1, 1, minus 1,
Yes.
minus 1,
Minus
1, minus 1, minus 1,
1.
And then one.
and then 1.
Is one.
Yeah.
So
I take
the sum will be 1, so it's a good start. It's a good start, but I don't know. I've never tried that, but thank you. You just ruined my weekend. Thank you.
I
will
should do that. Or maybe I help your jet lag.
Yeah. I'm kidding. No, it's a very good point.
Plus minus 1. Entries are plus minus.
Yes, plus minus 1.
That's why I'm saying.
So this is something to try definitely, and
Not the part, just the A.
you know, this is the kind of this so-called eureka moments. And in 2013, I had another eureka moment when a student came up to me and said, "Look at these two sequences; they sum to a constant. How is that possible?" I went back to Djokovic. How is that possible? He wrote the proof the next day. Yeah. So, yeah, this is, I have no idea, but this is something that easily can be checked in Maple. There's no doubt. I have all of the code to do that. I will get back to you. Okay, so there is another idea of now simultaneous decompressions, which is the following. Basically, this is in the PhD thesis of Jonathan Turner from Ohio. The idea of this simultaneous decompression is that if you have something like 77, for instance, which was an open problem since 2001, no one succeeded to find LP77, so 77, 7 times 11. His idea was to do 7 compression and to combine it with 11 compression and do somehow a simultaneous decompression. The details are in his PhD thesis. It's a few hundred pages. So we ended up. He came to Waterloo. He visited me. He came to the office at 9 in the morning every night. He's a U.S. Marine or captain of the Air Force captain. And we worked very hard, and we ended up in this paper with two other guys to find the only known example of LP77, which was open since 2001. And in any case, you can think, okay, you found LP77 and so what? But this solution revealed another property which is interesting in its own right, and we try to investigate it. So if you do this 11 compression of this LP77, then you find these nice small sequences of length 7 each. And if you compute the paths over here, the paths are constant, minus 21, minus 21, minus 21. And similarly, the paths are constant here, minus 1, minus 1, minus 1. This time it was me who noticed this. For once, I noticed something. And I came back to my co-authors and said, this cannot be a coincidence that these compressed sequences have constant path. Of course, the sum is minus 22 because it's minus 2 times 11. So there's not that many choices for this kind of decomposition. So we sort of elaborated this property in another paper in Journal Combinatorial Designs with another German mathematician who works in Austria, Christoph Kuchan. We elaborated this path constancy property for an arbitrary divisor M of the order L of the Legendre pair, and this is what we sort of proved. If the M compression of A comma B that we call calligraphic A and calligraphic B is made up of two constant path sequences of length n, we have this property here, then the PSD values at integer multiples of M of A and B are integers, and moreover they have the explicit evaluations, these ones here. So PSD A at M comma S for every S from 1 to n minus 1 over 2 is given by this second power sum of the squares of calligraphic A minus the first path value, and similarly for B. So we sort of uncovered that this property here has this very significant consequence for computational purposes, because now we have all these 1 to n minus 1 over 2 filters that we can use in any code that is searching for Legendre pairs. We have a series of n minus 1 over 2 if statements that will check whether this is correct. And if it isn't, we discard the candidate pair of sequences from the computation. So this is why doing these computational examples, if you like, and looking at their properties, this is why I think it's important, because you end up with, for example, some nice result like this. And we also did a couple of other things in that paper which are important. We determined the complete spectrum of the L over third value of the DFT or the PSD for any Legendre pair L, if L is a multiple of 3. For example, let's say you're looking for this L equals 117, 3 times 39, then it turns out that the PSD value of A at 39 and the PSD value of B at 39 can only be these 3 pairs of values. And that's an amazing restriction. Now you can run 3 parallel programs, one for this one for this one for this one, and lo and behold, you discover your LP117. This is a very stringent requirement, that the PSD of A is equal to 28 exactly, and the PSD of B is 208, or these other values. Of course, the sum is always 2 times 117 plus 2. That's so we ended up with the state of the art of these 12 integers in the range less than 200, for which the question of existence of Legendre pairs remained unresolved, and here they are. And well, in the meantime, this one and this one are stricken out. We end up with 10 values, and if you look at them, 5 of them are multiples of 4. This one, over here, and over here. 5 of them multiples of 5. Sorry. So we focused on another paper on some other conjecture on what could be the PSD value of L over 5 if L is a multiple of 4, and we found that it has this very specific form. It's L plus 1 plus square root of 5 over 2 times x, and then L plus 1 minus square root of 5 over 2 times the same x. So if you add them up, this will cancel out, and you get the 12 plus 2. So we ended up with this, we found the 85 using this conjecture, and we ended up with this 10 integers, which are still open cases, so no one knows if a Legendre pair of order 115 exists. We believe that it does, obviously. And finally, I wanted to finish, I think it's time, right, with this open problem here that has to do with multiplication theorems. So there was a combinatorial mathematician named Richard Turin, who is known in the world of sequences and the like. And he noticed this multiplication theorem for Golay pairs. So a Golay pair is simply a pair of sequences, again with plus and minus 1 value, but now the sum of the aperiodic autocorrelation coefficients is equal to 0 and not minus 2. So he used this notation. From a sequence, you get this discrete generating function over here that in combinatorics is called whole polynomial. So from this sequence, you get the discrete generating function. And he noticed that if A and B is a Golay pair of order G, and CD is a Golay pair of length V, order or length V, then the product pair E comma F is a Golay pair of order G times B. And this is the discrete generating function for this E, this one here, using the generating functions of A, B, C, and D. And this is the generating function for F. So it's a pretty interesting formula. And the paper is not very telling how he found it. It's just there. And if you do all the manipulations, it works. That these E and F have aperiodic autocorrelation 0. And with Djokovic, we noticed something, a small improvement, if you like, that if A and B is a Golay pair of length G and CD is a periodic Golay pair of length V. So in this C and D, the sum of the puffs now is 0. Then Turin's pair E and F is also a periodic Golay pair of length G times B. So this type of result is called multiplication theorem, and to find the multiplication theorem for Legendre pairs, I think is an open problem that would be nice to have. There is no multiplication theorem for Legendre pairs, whether or not you use a discrete generating function or a whole polynomial or anything else. There is nothing that says if you have LP n, LPM, then LP n times m. There's nothing like that, except for twin primes, P and P plus 2. But this is a very specific result. Even to do P times P plus 4 would be desirable, as we were discussing. But I think my time is up, so I will stop here. And thank you for your attention and for the questions.
Okay.
Just about this type of question.
Yeah.
So if you don't even know when one of the factors is like 2 or something, because in Hadamard matrices, the first thing we know is how to double this.
Yeah.
So
The Sylvester, you can from Hadamard, I mean the product construction.
Right.
The product, if you have Hadamard matrix of order n, and you take the tensor product with a Hadamard matrix of order m, then you get Hadamard matrix of order n times m. The tensor product, the Kronecker tensor product is enough. But for Legendre pairs, that doesn't work, because they have this constant minus 2. That's the inherent difficulty in there. Here the constant is not minus 2. The constant is 0. For Golay pairs, the autocorrelation constant is 0. So that simplifies a lot of things in this monster formula here, which somehow magically magically works, right? But this magic breaks down when you use it for Legendre pairs, or even to adapt it. How would you adapt this to make it work for Legendre pairs? It's not clear. I guess you have to look at the anatomy of this proof, but the proof is not very. He doesn't say how he discovered it. He just you know. It's a series of manipulations, and in the end, everything works out, and you get that this ENF that they have periodic autocorrelation function 0, summing to 0. So it is a Golay pair.
Okay.
Thank you.
Again. As you can hear from the noise, there's already coffee